Welcome to Top 5 HQ, the series. Tonight, we journey to the very edge of the unknown. In a universe filled with light, wonder, and motion. There exist places so dark, so dense, and so mysterious, that not even light can escape their grasp. These are black holes. They defy our understanding of physics, warp time and space, and hold the power to reshape galaxies, or erase them entirely. Born from the death of stars, hidden in the hearts of galaxies, and drifting silently through the void. Black holes are the most extreme phenomena we've ever discovered, and the least understood. In this episode of Top 5 HQ, the series, we'll dive into the science, the history, and the mind-bending mysteries of these cosmic monsters. Because to understand black holes is to stare into the very fabric of reality itself. Are you ready to explore the darkness? Let's begin. Before we had images of glowing accretion disks, before Einstein bent time and space, before we even knew the term black hole, there was a man with an idea. An idea that was so far ahead of its time, it would go unproven for over 150 years. His name was John Michell. In 1783, Michell, a British natural philosopher, geologist, and clergyman, proposed something truly revolutionary: the existence of dark stars. These were hypothetical celestial bodies so massive and so dense that their gravitational pull would be so strong, even light itself couldn't escape. That's right, before we even understood what a photon was. Michell was imagining objects invisible to the naked eye, hidden not because they were small, but because they were powerful beyond comprehension. How did he come up with this? Michell combined Isaac Newton's laws of motion and gravity with the then popular corpuscular theory of light. The idea that light behaved like tiny particles. If light was made of particles, and gravity pulled on all particles, then a star could, in theory, pull on light just like it pulls on rocks, water, or planets. He even did the math. Using Newtonian mechanics, Michell calculated that if a star's mass was about 500 times that of the Sun, and its radius was comparable, the escape velocity, the speed needed to break free from its gravity, would exceed the speed of light. No light, no visibility. Just a dark object drifting through space, betraying its presence only by its effects on other bodies. And he didn't stop there. Michell suggested that if these dark stars existed, we might be able to detect them indirectly, by observing their gravitational influence on nearby stars. In other words, he was imagining gravitational lensing and binary systems, centuries before modern astrophysics developed the tools to confirm such phenomena. Unfortunately, the idea of dark stars didn't gain much traction in the scientific community at the time. It was simply too abstract, too speculative. After all, the speed of light wasn't even accurately measured, and the nature of light itself was still being debated. Then came the 20th century. Fast forward to 1915, and Albert Einstein releases his general theory of relativity, a framework for understanding how gravity actually bends the fabric of space-time. Suddenly, the idea of extremely massive, compact objects trapping light wasn't science fiction, it was a mathematical reality. Just a year later, in 1916, German physicist Karl Schwarzschild would find a solution to Einstein's equations that described what we now recognize as a black hole. But John Michell's name had nearly vanished from the conversation. It wasn't until the late 20th century that historians of science revisited Michell's work and realized how incredibly far ahead of his time he truly was. Today, he is remembered not only as the man who first predicted black holes, but also as one of the most visionary thinkers of the Enlightenment era. So, the next time we look at an image of a black hole's shadow, or detect gravitational waves from colliding giants in space, we should remember that this story began over 240 years ago, with a quiet scholar, a simple equation, and a bold idea. What if there are stars so powerful even light can't escape? Jean-Michel's vision of dark stars faded into obscurity for over a century. But the story of black holes didn't end with him. It was only just beginning. In 1915, a man whose name would become synonymous with genius introduced a theory that would forever reshape our understanding of the universe. That man was Albert Einstein, and his groundbreaking idea was the general theory of relativity, where Newton saw gravity as a force between two masses. Einstein revealed a much deeper truth. Gravity is the curvature of space-time itself. Massive objects like stars and planets don't pull on things in the traditional sense. Instead, they warp the very fabric of space and time, creating curves and dips that guide the motion of everything around them. It was a revolutionary leap, a cosmic game-changer. Einstein's equations allowed scientists to model how massive bodies interact with space-time. And almost immediately, those equations hinted at something incredible and terrifying. A German physicist named Karl Schwarzschild, while serving on the Eastern Front during World War I, found a precise mathematical solution to Einstein's field equations. His solution described what would happen if an object became infinitely compact. If all its mass were squeezed into a single point, this hypothetical object would warp space-time so severely that nothing, not even light, could escape its pull. It was the modern mathematical birth of what we now call a black hole. But here's the twist. Einstein himself was skeptical. Despite the implications of his own theory, Einstein did not believe black holes could exist in reality. He thought they were strange but unrealistic mathematical artifacts, curiosities of the equation rather than real cosmic phenomena. After all, how could nature allow such an extreme, monstrous object to form? One where time slows to a stop, where density becomes infinite, where the laws of physics begin to break down? It was simply too bizarre. And yet, the math was relentless. Over the next several decades, physicists continued to explore Einstein's equations, uncovering that these objects weren't just possible. They were inevitable outcomes of massive stars collapsing under their own gravity. Einstein may have opened the door, but it would take decades. And the rise of astrophysics, radio telescopes, and space observation. Before the scientific world fully embraced the reality of black holes. Today, we know that Einstein's equations predicted some of the universe's most extreme and fascinating phenomena. Gravitational waves, time dilation, event horizons, and, yes, black holes. It's a profound irony that the man who gave us the blueprint for black holes never lived to see the smoking gun. Never saw the jets of light bursting from their edges or the iconic image of the shadow cast by a supermassive one in galaxy M87. But his theory lives on, not just as an equation, but as a window into the darkest corners of the universe. And from those corners, the story only gets stranger. For decades after Einstein's theory and Schwarzschild's calculations, these strange cosmic beasts remained unnamed, undefined, and even dismissed. Some scientists referred to them as frozen stars, while others called them collapsars or simply singularities. The concept was out there, mathematically sound, theoretically fascinating. But it lacked something essential. A name that captured the imagination. That all changed in 1967, thanks to a brilliant and bold physicist named John Archibald Wheeler. During a lecture on the physics of gravitational collapse, Wheeler found himself searching for a more compelling term to describe the ultimate endpoint of a collapsing star. A place where gravity becomes so overwhelming, not even light can escape. A place beyond space and time, utterly black, utterly final. And then, like a gravitational wave through scientific language, it came to him. Black hole. Two simple words, monumental impact. The term immediately resonated with the scientific community and the public. It was stark, evocative, and chilling. Black hole described not just an object, but a cosmic mystery, a gateway to the unknown. A region from which no information, no light, no matter, nothing could return. It was a turning point. Wheeler didn't just coin a phrase, he gave the phenomenon its identity, one that was finally worthy of its power and presence in the universe. From that moment on, black holes were no longer just obscure solutions to Einstein's equations. They were celestial legends, the dark hearts of galaxies, the ultimate edge of physics. And the world started to take notice. With this new name came renewed curiosity, bold research, and groundbreaking discoveries. Telescopes pointed skyward. Scientists began hunting for the telltale signs. Stars that wobbled around invisible centers, bursts of X-rays from accretion disks, and strange gravitational anomalies. The black hole was no longer just theory. It was on the map. It was real. A name had opened the door. And what lay beyond was more incredible than anyone had imagined. Because black holes don't come in just one size. In fact, they exist on a scale so wide, it defies belief. From the unimaginably tiny to the galactically massive, black holes occupy every corner of the cosmic size chart. Let's start with the theoretical end of the spectrum, micro-black holes. These are purely hypothetical. Predicted by some theories of quantum gravity and extra dimensions. Unlike their monstrous counterparts, these black holes could be smaller than an atom, yet still contain an incredible amount of mass. If they exist, they might have formed during the Big Bang. And they could be zipping around space right now, too small to see, yet too dense to ignore. Some even speculate they could be created in high-energy environments, like particle collisions. Spoiler, it didn't. But the theory still fascinates scientists. Because micro-black holes might hold the key to unifying quantum physics with general relativity, a theory of everything. Now jump to the other extreme. The supermassive black holes. These are the cosmic titans. Each one contains the mass of millions, or even billions, of suns. All crushed into a single, compact point. They're not just massive. They're central to the structure of entire galaxies. The Milky Way? It has one of these monsters. Sagittarius A at its very core. And in the galaxy M87, astronomers captured the image of another supermassive black hole with a mass more than 6.5 billion times that of our Sun. To put it simply, if the Sun were a marble, this black hole would be a mountain range made of pure gravity. And somewhere in between? There are stellar mass black holes, born from the collapse of massive stars. And the elusive intermediate black holes, the mysterious missing link scientists are still trying to prove. What all these black holes have in common is this. No matter their size, they represent extremes of nature. Limitless gravity, crushed space, and warped time. From the tiniest theoretical speck to the largest gravitational behemoths in the universe. Black holes come in all shapes and sizes. But every one of them challenges what we think we know about the cosmos. One truth remains. Where there's a galaxy, there's a black hole. In fact, astronomers have discovered something astounding. Every large galaxy in the universe appears to have a supermassive black hole at its core. Take our own galaxy, the Milky Way. At the very center of it all, 26,000 light-years from Earth, lurks a silent titan known as Sagittarius A. It weighs in at over 4 million times the mass of the Sun. And we know it's there because of how it tosses nearby stars around like toys in a whirlpool. One star, known as S2, orbits Sagittarius A in a 16-year elliptical path. Proof of a powerful, unseen force anchoring the heart of our galaxy. And it's not just us. In the giant elliptical galaxy M87, The supermassive black hole at its center weighs an unfathomable 6.5 billion solar masses. In NGC 4889, a distant galaxy in the Coma cluster, the central black hole could tip the scale at 21 billion solar masses. These are cosmic juggernauts, black holes so large they defy comprehension. Yet they sit quietly at the center of their galaxies, holding them together like gravitational glue. But here's where it gets even more fascinating. Scientists now believe they may have played a crucial role in the formation of galaxies themselves. It's possible that supermassive black holes and galaxies grew up together, shaping and influencing one another through gravitational interactions, feeding frenzies, and bursts of energy. Think about that for a moment. What if black holes aren't just cosmic anomalies, but cosmic architects? Today, astronomers are using telescopes like the James Webb Space Telescope and radio arrays like the Event Horizon Telescope to study galactic centers all over the universe. And in nearly every case, the pattern holds. Where there's light, there's a shadow. Where there's a galaxy, there's a black hole. But these aren't just anchors of matter and gravity. They're warpers of reality itself. Because black holes don't just bend space, they bend time. This is where the story gets truly strange and truly real. According to Einstein's general theory of relativity, the presence of mass, especially extreme mass, like that found in black holes, distorts the fabric of space-time. Imagine space and time as a single woven sheet. A star might cause a dip. A planet might ripple it slightly. But a black hole? A black hole rips it downward, stretching and warping it into a near-bottomless pit. This isn't science fiction, this is physics. The closer you get to a black hole, the more intense this warping becomes. At a certain point, known as the event horizon, light itself cannot escape. But even before that boundary, something even stranger happens. Time slows down. To an outside observer, someone falling into a black hole would appear to move in slow motion. As they approach the event horizon, time would stretch, slow, and eventually appear to freeze. As if they're trapped in a moment, forever suspended at the edge of the abyss. Meanwhile, for the person falling in, time would continue normally for them, until they cross that final boundary, never to return. This phenomenon is known as gravitational time dilation, and it's been proven, not just around black holes, but in real experiments here on Earth and in orbit. Even astronauts aboard the International Space Station age ever so slightly slower than we do on the surface. It's a tiny effect on Earth. But around a black hole, it becomes extreme. In fact, this is the very concept featured in films like Interstellar, where time on a planet near a black hole moves radically slower than it does elsewhere. It sounds like fantasy, but it's based on real physics. Black holes don't just destroy, they reshape the rules of reality. They stretch time. They bend space. They show us that the universe is far more fluid, far more strange, than our everyday senses can perceive. And the deeper we fall into their mysteries, the more we realize that time itself is not as constant as we once believed. They challenge everything we thought we knew about reality. And yet, we've never actually seen one. Because by their very nature, black holes are invisible. They emit no light, no color, no radiation that our eyes, or even the most advanced telescopes, can detect directly. So how do we know they're real? It's one of the great scientific triumphs of our time. Learning how to see the invisible. Black holes don't glow, but they influence everything around them. They tug on nearby stars, altering orbits in ways that can only be explained by an unseen, ultramassive object. They tear apart gas clouds and feed on matter, creating intense friction and radiation in the process. Surrounding many black holes is what's called an accretion disk, a spinning whirlpool of superheated gas, dust, and debris spiraling toward the event horizon. As the material is pulled in, it heats up to millions of degrees, producing X-rays and other high-energy radiation that we can detect from Earth. In other words, we don't see the black hole. We see what happens right before something disappears into it forever. And in 2019, humanity achieved something once thought impossible. We captured the first ever image of a black hole's shadow. Using a global network of radio telescopes called the Event Horizon Telescope. Scientists peered 55 million light-years away, into the heart of galaxy M87. What they found was astonishing. A glowing, fiery ring of gas and dust, curving around a perfectly dark circle. That dark void? That was the black hole's shadow, cast on the surrounding light by the warping of space itself. It wasn't a photograph in the traditional sense. It was the result of years of data collection, radio wave readings, and computational imaging. But it was real. The first direct visual evidence of a black hole. An object once thought to be a mere mathematical fantasy, now stared back at us from the abyss. We may never see the heart of a black hole. But thanks to modern science, we've learned to trace its silhouette, to map the chaos around it, and to recognize its presence through gravity, motion, and light bent to its limit. Because in a universe this vast and strange, even the things we can't see can shape everything we do. We may not be able to see black holes directly. But in 2019, we did the next best thing. We captured the shadow of one. It was a moment that marked a turning point in human history. April 10, 2019, the day scientists unveiled the first ever image of a black hole. An achievement once thought impossible had become a reality. The black hole in question was located in the heart of a galaxy called Messier 87, or M87. A giant elliptical galaxy some 55 million light-years from Earth. At the center of this galaxy sits a supermassive black hole, one of the largest ever discovered, tipping the scales at over 6.5 billion times the mass of the Sun. And for the first time, we saw it. But how? This wasn't done with a single telescope. It took a global network of radio telescopes working together in perfect synchronization. Known as the Event Horizon Telescope, or EHT. From the peaks of Hawaii to the mountains of Chile. From Spain to Antarctica. 8 powerful observatories were linked together using a technique called Very Long Baseline Interferometry. It allowed them to function as one Earth-sized virtual telescope. For 5 days in April 2017, they all turned their gaze toward the heart of M87, collecting massive amounts of radio wave data. So much, in fact, it had to be physically shipped on hard drives rather than sent over the internet. It took 2 years of processing, algorithms, and cross-validation to stitch together a picture of something that doesn't emit light, doesn't reflect anything, and exists in the far reaches of space. And then it appeared. A glowing, golden-orange ring, like a cosmic halo, surrounding a perfect circle of darkness. This was the shadow of the black hole. A silhouette cast by the warping of light at the edge of the event horizon. It wasn't a fantasy, a simulation, or a theory. It was evidence. The strongest we've ever had that black holes are real. But this wasn't just about proving their existence. It was about testing the limits of physics. The image matched exactly what Einstein's general relativity predicted, down to the size and shape of the shadow. It was one of the most extraordinary confirmations of his theory, over a century after he published it. And in the process, the world saw something no human had ever seen before. A piece of the cosmos that had, until then, only lived in numbers, equations, and imagination. The moment was historic. News outlets around the world shared the image. Social media lit up. And people, regardless of background, stopped for a moment to stare into the unknown. This wasn't just a scientific achievement. It was a reminder that we, here on our tiny pale blue dot, are capable of extraordinary things when we look up and work together. We had seen their shadow. We had traced their presence in stars and gas. But in 2015, for the first time in history, we heard them. Two black holes. Invisible, silent, distant. Spinning around one another in a death spiral, until they finally collided. And when they did, they shook the fabric of reality itself. This is the story of black hole collisions. One of the most powerful, violent, and awe-inspiring events in the known universe. It begins with a prediction made by Albert Einstein in 1916. According to his theory of general relativity, massive objects accelerating through space would create ripples in space-time. Tiny waves moving at the speed of light. He called them gravitational waves. But for decades, scientists believed they would be too small to ever detect. A ripple from a colliding star system might move a detector's laser by less than the width of a proton. It seemed impossible. Until it wasn't. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory. A massive scientific experiment with two facilities in the United States. Each one uses twin laser arms stretching over 4 kilometers long, bouncing light between mirrors with atomic precision. On September 14, 2015, those lasers twitched. Ever so slightly. But unmistakably, LIGO had detected a gravitational wave. The source? Two black holes, one about 29 times the mass of the Sun. The other 36 had spiraled into one another and merged. The impact released more energy in a fraction of a second than all the stars in the observable universe combined. Not as light, not as heat, but as gravitational waves, pure ripples in the fabric of space itself. We didn't see the collision, but we felt it. And just like that, a new era of astronomy was born. Since that day, dozens more black hole mergers have been detected. Each one gives us clues about their masses, their spins, their distances, and the invisible forces shaping the cosmos. Even more fascinating? Some of these collisions may involve intermediate mass black holes, which scientists are only beginning to understand. And others suggest that black holes might be forming and merging far more often than we ever imagined. These aren't slow processes. These are cataclysmic events, sending shockwaves across billions of light years. Ripples that, against all odds, reach us here on Earth. Black holes may be silent. They may be invisible. But when they collide, the universe trembles. But when something, or someone, falls into one, that's when things get truly strange. Because a black hole doesn't just trap light. It tears apart reality itself. This is the story of spaghettification. One of the most mind-bending, real, and horrifying consequences of a black hole's gravity. Let's imagine, for a moment, that you're drifting through space. Ahead of you is a black hole. Silent, dark, beautiful, in the most terrifying way. As you approach, gravity begins to pull. At first, it feels like any other massive object. Until you get closer. Then, something strange happens. Your feet, being slightly closer to the black hole than your head, experience more gravitational force. Not just a little more, but a rapidly increasing difference in pull. This isn't your typical tug-of-war. This is tidal force, on a level your body can't withstand. Your body begins to stretch, elongate, pull apart. First your legs, then your spine, then your brain. You become a strand, thin, elongated, and helpless. Like a piece of spaghetti. Hence the name, spaghettification. It's not science fiction. It's a real physical process, predicted by general relativity, and known to occur in regions of extreme gravitational gradients, like near a stellar mass black hole. Now here's the eerie part. If someone were watching from a distance, they'd never see you cross the event horizon. Time dilation would cause your descent to appear slower and slower, until you seemed frozen just at the edge. But from your perspective, you'd fall right in, stretch thinner and thinner, until you reach the singularity, the point at the center where density becomes infinite and the laws of physics break down entirely. Spaghettification wouldn't happen the same way with every black hole. Near supermassive black holes, like Sagittarius A at the center of our galaxy, the tidal forces near the event horizon might actually be weaker, meaning you could pass the horizon unharmed for a while. But eventually, whether quickly or gradually, gravity wins, and you become a noodle. In the universe of black holes, death doesn't come with fire or explosion. It comes with silence, distortion, and an unimaginable stretch of space and time. So if you ever find yourself nearing a black hole, don't reach for a rope. Reach for a pasta pun. Because this is how the universe makes spaghetti. For a place from which nothing can escape. Black holes sure know how to make a scene. Because while they trap light, bend time, and stretch matter into noodles, some black holes do something even more spectacular. They shoot out jets, beams of pure energy, that stretch across entire galaxies. Yes, you heard that right. From the darkest objects in the universe come some of the brightest displays ever recorded. Let's break it down. These jets are called relativistic jets. Colossal, focused streams of charged particles blasted into space at nearly the speed of light. They don't come from inside the black hole, but from the chaotic region just outside it, known as the accretion disk. As matter spirals toward the event horizon, it spins faster and faster, compressing, heating, and tearing itself apart. Temperatures rise to millions of degrees. Magnetic fields twist like whirlwinds. The energy becomes unstable, focused, and finally, ejected in two towering columns. One above, one below. Plasma is hurled out into space, creating jets so long they can span hundreds of thousands, even millions of light years. That's like a flashlight beam from Earth, reaching past the edge of the galaxy. And yet, it comes from a region smaller than our solar system. One of the most famous examples? The galaxy Hercules A. At its core lies a supermassive black hole that's blasting out jets of energy spanning over 1.5 million light-years. Larger than 15 Milky Ways lined up in a row. We see these jets in X-ray and radio wavelengths. Vast, luminous threads of energy glowing against the backdrop of deep space. But here's the real mystery. Scientists still don't fully understand how these jets form with such precision. How does something as chaotic as a black hole's feeding frenzy create something so narrow, so focused, so powerful? It's one of the greatest unsolved puzzles in astrophysics. And yet, there it is. Nature's contradiction. A place that traps everything, and somehow becomes the loudest beacon in the cosmos. So the next time you picture a black hole as a silent, invisible void, remember this. Some black holes don't just consume the universe. They announce themselves with cosmic firepower. They bend time. They stretch matter. They even launch jets of energy across the universe. But for all the chaos that surrounds a black hole, there's one boundary that defines everything: the event horizon. It's a term that sounds like science fiction, but it's one of the most fundamental and terrifying realities in astrophysics. The event horizon is not a surface. It's not made of matter or energy. You won't crash into it or feel it passing over your skin. Instead, it's a boundary in space-time. A silent, invisible line that marks the edge of no return. Once something crosses this threshold, be it a star, a spaceship, or even a photon of light, there is no going back. Not even light, traveling at the fastest speed in the universe, can escape. That's why black holes are black. They trap all information beyond the horizon. From the outside, anything falling in appears to slow down, thanks to gravitational time dilation. It stretches, it dims, and it eventually freezes in time at the edge, never quite disappearing. But that's just what an outside observer sees. From the perspective of the object falling in, it crosses the horizon in finite time, and then falls unstoppably toward the singularity at the center, where physics, as we understand it, ceases to function. The event horizon is often described as the ultimate one-way door, a cosmic trapdoor, a place where space folds inward, and the past, present, and future collapse into one strange, inescapable now. But here's the kicker. We don't fully know what happens beyond it. Some theories suggest the information is lost forever. Others, like Stephen Hawking's, propose that black holes slowly leak information through a faint glow of quantum particles, a concept known as Hawking radiation. And that leads to one of the greatest puzzles in modern science: the black hole information paradox. If nothing escapes, if information is lost, does that violate the fundamental rules of quantum mechanics? It's a paradox that continues to drive the world's brightest minds to the edge of physics, in search of a theory that can unite gravity and quantum reality. One thing is certain: the event horizon is more than a boundary. It's the veil between the known and the unknowable, a line in the cosmos where the laws of nature change forever. The event horizon is the point of no return, a boundary so absolute, not even light can escape. For decades, we believed that nothing, not a single particle, could ever come back from beyond that veil. But then, in the 1970s, a single idea sent shockwaves through the world of science. An idea that dared to ask, what if black holes die? That idea came from one of the most brilliant minds in history, Stephen Hawking. Hawking combined Einstein's general relativity with quantum field theory, and what he discovered was extraordinary. Under the right conditions, black holes could emit radiation. Yes, emit radiation. This was the birth of a radical concept now known as Hawking radiation. Here's how it works, in simple terms. According to quantum physics, empty space isn't really empty. It's a seething, jittery field of energy, constantly producing virtual particle pairs. One matter particle and one antimatter particle, that pop into existence for the briefest moment before annihilating each other. But near the event horizon of a black hole, something strange happens. If a virtual pair forms right on the edge, it's possible for one particle to fall into the black hole, while the other escapes into space. From an outside observer's point of view, it appears as if the black hole is emitting a real particle, as if it's glowing ever so faintly. This glow is Hawking radiation. And over billions and trillions of years, this radiation causes the black hole to lose mass, slowly evaporating, shrinking, and eventually, if left undisturbed, disappearing entirely. That's right. A black hole, once thought to be eternal, can fade away. But this leads to a cosmic conundrum. If black holes evaporate, what happens to all the information that fell inside? Is it gone forever? That would violate a core principle of quantum mechanics. That information can't be destroyed. This paradox, known as the black hole information paradox, has sparked decades of debate. Hawking himself changed his position over time. And the mystery remains unsolved to this day. Are black holes truly destroyers of information? Or are they cosmic libraries, slowly leaking their knowledge back into the universe? We don't yet know. But what we do know is this: even the darkest objects in the cosmos may not be forever. Even the most powerful engines of gravity might one day fizzle into nothingness. Stephen Hawking showed us that black holes aren't just the end. They're part of a cosmic life cycle, where even darkness has an expiration date. Stephen Hawking revealed that black holes might not last forever. But before they can fade, they must be born. And one of the most common ways a black hole comes into existence? It begins with a star's final breath. These are known as stellar mass black holes. And they form in the aftermath of one of the most violent events in the universe, a supernova. Let's break it down. Stars, like our sun, shine because they're constantly fusing hydrogen into helium in their cores. This nuclear fusion creates an outward pressure that balances the inward pull of gravity. But when a star is massive enough, at least 20 to 30 times the mass of our sun, it eventually runs out of fuel. Hydrogen burns out, then helium. Then heavier elements, like carbon, oxygen, and even iron. And then fusion stops. Without that outward force, gravity wins. The star's core collapses inward in an instant. Matter crushed tighter and tighter under its own unimaginable weight. The outer layers explode in a brilliant supernova, briefly outshining entire galaxies. But deep at the core, what remains is not a shining ember. It is a gravitational singularity. A place where density becomes infinite, and space itself folds in. A black hole is born. These stellar mass black holes are typically between 5 to 20 solar masses. They're the most common type in our universe. And they can be found scattered throughout the Milky Way. Hidden, invisible, silent. But we've detected them. Not by sight, but by watching how they affect other stars. In binary systems, a black hole can pull material from a companion star, creating an accretion disk that glows in X-rays. This is how we found dozens of stellar black holes. And we know there are likely millions more, drifting alone through the galaxy, undetected. And get this. One stellar mass black hole, Cygnus X1, discovered in the 1960s, was the first confirmed black hole ever found. It was so strange at the time that even Stephen Hawking bet against its existence, and later admitted he lost. These black holes are the endpoints of stellar life. But in a way, they're also the beginning. Because in their gravity, they shape galaxies. In their collapse, they seed supernovae that spread elements like iron and gold across space. And in their silence, they tell the story of a star that once burned bright, and now bends reality itself. Some black holes are born in brilliant explosions. Others form at the hearts of galaxies, shaping the orbits of billions of stars. But not all black holes stay in place. Some are out there, alone, wandering, invisible, silent, and dangerously close. These are the rogue black holes. Dark remnants of collapsed stars that no longer orbit anything. They're like cosmic ghosts, drifting through space, undetectable to the naked eye or even the most advanced telescopes, unless they happen to interact with something. And scientists believe there may be millions of them in our galaxy alone. When a massive star explodes in a supernova, the core collapses into a black hole. But the force of that explosion isn't always symmetrical. Sometimes, it delivers a gravitational kick, flinging the newly born black hole out of its place. Untethered, these black holes roam the galaxy, pulled only by the faint tug of gravity from distant stars or dark matter. And here's the unnerving part. They could be passing through star systems right now, possibly even near ours. One could be drifting silently through the outer regions of the Milky Way, or hiding in the vastness beyond the Kuiper Belt. Completely invisible, yet capable of devouring anything it comes too close to. But detecting one? That's the real challenge. Because unless a rogue black hole interacts with a star, or passes in front of a distant light source, bending the light through gravitational lensing, it leaves no trace. And yet, in 2022, scientists using the Hubble Space Telescope may have finally captured evidence of such a rogue. A stellar mass black hole drifting alone, 5,000 light-years away in the constellation Sagittarius. If confirmed, it would be the first solitary black hole ever directly detected. A shadow, moving through space, pulling on nothing, seen only by the way it bends the stars behind it. It's a chilling reminder that black holes are not confined to the centers of galaxies, or the hearts of supernovae. They are out there, everywhere. Some locked in place, some flying free through the dark. Rogue black holes, the unseen travelers of our galaxy. And there you have it. From collapsing stars and time-warping gravity, to rogue giants drifting silently through space, black holes are more than just cosmic mysteries. They're the universe's most powerful forces, shaping galaxies, bending light, and challenging everything we think we know about physics. Whether they're creating jets that stretch across space, or slowly evaporating through Hawking radiation, one thing is certain. Black holes aren't just the end of the story. They might be the key to understanding how the story even began. If you enjoyed this journey into the darkest corners of the universe, don't forget to like, subscribe, and hit that notification bell so you never miss an episode of Top 5 HQ, the series. And if you're watching on Rumble, follow, share, and spread the curiosity. Until next time, stay curious, stay bold, and keep looking up.